Okay, but let's now just talk about this idea of work. And for work, we've got this formula F change in x cos theta, and we've got to really understand what each part of this formula means. So the F is going to be the force that we're calculating the work of. So if this F is friction, then we're calculating the work done by friction. If that F is gravity, then you'd be calculating the work done by gravity, right? This change in x is the displacement of the object, and then very importantly, this theta is the angle between these two vectors, the force and the displacement, right? So don't confuse that theta for the angle of the incline, for example. That's not what we mean by theta. Theta is the angle between the force and the displacement. Okay, so let's say, for example, we've got this force of 10 newtons and we've got a displacement of, let's say, 5 meters. So to calculate the work done by this force, we've got to go F times the change in x times cos of the angle between these two vectors. Now, if two things are pointing in exactly the same direction, the angle between them is going to be 0 degrees. And cos of 0 is 1, so this is just going to be the 10 times 5 is 50 joules. Okay, so this force would have done 50 joules of work. Now, in this second sort of example here, the force is going upwards, displacement is going this way, and you can see that this will be a 90-degree angle between these two things, right? Now, here, if we use the same things, the force as 10 newtons and the displacement as 5 meters, then we can go calculate the work done here. So the work done is going to be 10 times 5 times cos of the angle between these two things. And the angle between those two things is 90 degrees, and cos of 90 is actually 0. So this is going to give us work done of 0 joules. Okay. Now, this here, for example, is something that we see frequently with the normal force. Because if something is moving parallel or along a surface, then it's always going to be perpendicular to the normal force, which means the normal force won't be doing any work, right? So a way that I think about it internally is I ask myself, does this help or does this hinder? Now, this force at this 90-degree angle is definitely not helping it going that way, so it's not doing any positive work. But it's also not hindering it. And so if it neither helps nor hinders the object in actually covering that displacement, then it's not going to be doing any work. Okay, so what about this next one here? Let's say we've got a 30-degree angle like that. Well, now the work done would be the 10 times the 5 times now cos of 30. Right, so here if you go 10 times 5 times cos of 30 degrees, then you'd get an answer of 43,30 joules. Okay, and that would then be the work done by that F, right? Now, another way to think about this is to say that only the component of the force in the line of action of the displacement is actually going to be doing any work. So this force here, right, we know can be broken up into an x component and a y component. But as we just said, something that's acting at 90 degrees to the displacement is not doing any work. So in terms of this force, this component of the force does not do work, whereas this component of the force is the component of the force that's actually doing the work, right? So even though this one was 10 newtons and this one was 10 newtons, we found that in this example below, the work done was less, and that was because only a component of the force, the x component, was actually doing work. Whereas in the first example, all of the force was in the direction of the displacement, and so all of that force was actually doing the work. You don't have a passenger or whatever you want to call it, like we have here with this y component that's not doing any work. Okay? And then we've got to go and figure out how to find the work for this next example. So for the next example, what's interesting is that these two things are pointing in different directions. Okay, so if they're pointing in different directions, the angle between them isn't 0, it's actually going to be 180 degrees, right? Because if they start pointing in the same direction and then you've got to move one so that they point in opposite directions, you've got to have 180 degrees as the angle between them. So this is going to be 10 times 5 times cos of 180, right? And that is actually going to be negative 50 joules, right? So this then asks us the question, well, is work then a vector? Because we can have a positive answer and a negative answer, and the answer is no, work is not a vector. It is in fact a scalar. The positive and the negative is actually referring to energy transfer, right? So positive work done is if something's actually adding energy to that object, whereas negative work done is when we're actually removing energy from the object, right? So it doesn't mean that it's a vector or a scalar that has a direction. Okay, so let's do this example here where we're going to go and find the work done by each and every force that is actually doing work on this object, right? So we've got this crate, the mass is 5 kilograms, and it's being pulled 10 meters up an incline by a force of 100 newtons. The frictional force is 20 newtons, and we have to calculate the work done by every force acting on the crate as well as the net work. Okay, so first things first, let's just understand what forces are actually acting on this crate, right? So you're going to have the applied force going up in that direction, the normal force will be going that way, friction will be opposing the motion, and then I'm going to break up gravity into Fg parallel and Fg perpendicular. Okay, so I have something that looks like that. Okay. So then what we have to do is start finding the work done by these forces, right? So first up, I'm going to find the work done by the applied force, and I'm going to call it WA, right? So F change in X, well, let's be thorough, let's write it down, cos theta, okay? And we know that it's a 100 Newton force, fantastic. We know that this object is displaced 10 meters up the incline, and then this should be cos of 30 because 30 degrees is that angle there of the incline. Okay, I'm hoping that you all cried out no, 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 that I've done the wrong thing here, right? Remember, the angle theta in W change in equals F change in X cos theta. That angle theta is the angle between the two vectors, the force and the displacement, right? So here, the displacement is in that direction and the force is in that direction. So this 20 degrees is in fact the angle between the force and the displacement, right? So here we'll go 100 times 10 times this cos of 20, and that is going to give us an answer of 939.69 joules. Okay. So that was the work done by the applied force. Then to find the work done by friction is going to be quite easy because we know that the frictional force is 20 newtons. So we can go 20 times the change in X, which is 10. But now cos is what? So we know that the displacement is up the slope and friction is acting opposite to the displacement. It's going down the slope. So this is a 180 degree angle, and so we've got to put in 180 here. All right, so 20 times 10 times cos 180 is going to give you an answer of negative 200 joules. Okay, so negative 200 joules, right? So what else do we have? We've got gravity. Okay. Right, so what I'm going to do now is possibly going to make you uncomfortable, but bear with me for a bit, right? So here, what I want to show you is that this formula always works as long as we're using the force, the displacement, and the angle between the force and the displacement, right? So gravity is going straight down, and I can see that that might not be easy to see, so let's go back to this. Okay, so gravity is going straight down, right? So the force of gravity we know is mg. So that's going to be the 5, the mass, times the 9.8. The displacement is still going to be the 10 meters, right? And now, because of what? Well, what's the angle between these two forces? So gravity is going straight down like that. The change in x is like that. And we can actually see that if we draw this horizontal here, this is 90 and this is the 30 degrees. So the angle between the force and the displacement is the 90 plus the 30, which is then 120. So this is then cos 120. Okay, right. Now I know that you're probably used to finding the components, and I am going to go through how to do that with gravity, but I just want to show here how versatile this formula is, and that it's always going to give you the right answer as long as you're using the force, the displacement, and the angle between the force and the displacement. And here we get an answer of negative 245 joules, okay? And then we've got to find the work done by every force acting on the crate. So which force have we left out? Yes, the normal force, right? Now here, the normal force, the work done by the normal force, is going to be equal to the magnitude of the normal force. Now the magnitude of the normal force we know we can find, but in order to do it, we've got to find the y component of the force, the applied force, Fg, perpendicular, what emission. I'm just going to write here normal times the change in x times cos of, and now here I know that the normal force is going to be perpendicular to that displacement because this thing is moving up the slope, and the normal is always perpendicular to the slope, so I know the work done by the normal force is going to be 0 joules. Okay, and then it says calculate the net work. Well, surely the net work is just the sum of the work done by all of these forces. It's going to be the positive work, the energy added by the applied force, minus the energy taken away by friction and gravity, right? So we're just going to go 939.69 minus the 200 minus the 245, and that is going to be our answer for the network that was done. Okay, and we're going to talk a little bit more about network in the time coming, but now it is going to be your turn to please pause the video and give this example a try. Okay, so we've got this crate. The mass is 3 kilograms. It's being pulled along a horizontal surface for a distance of 5 meters by a 40 Newton force, and that 40 Newton force is acting at an angle of 30 degrees to the horizontal. The coefficient of kinetic friction is given as 0,1. So A says find the work done by the applied force. Okay, now here we know that the work done by the applied force is equal to that applied force times the displacement times cos of the angle between the force and the displacement, which is going to be 40 times 5 times cos of 30 degrees. Okay, so they give us to that nicely. You can see that 30-degree angle between the force and the displacement. Good times. So 40 times 5 times cos of 30 gives us work done by the applied force of 173,210. Oh, now I wrote newtons. It's joules. Okay, joules. Okay. So then B, find the work done by the frictional force. Okay. So again, we can go do WF equals force of friction change in x cos theta, but it might be clear here that we don't yet know what the frictional force is. However, they did give us the coefficient of kinetic friction, and that is a little bit of a hint that they want us to use this. The force of friction is equal to the coefficient of kinetic friction times the normal force. I don't know why I wrote mu F, should be mu K. Okay, so here, in order to find the normal force, we've got to think, okay, what are all the forces that are acting in this perpendicular line of action, the up-down line of action, right? So you've got Fg going down, that's true, but then you also have the normal going up, but not just the normal, you also have the y component of the applied force that's going up. And since this object is moving rightwards, that means the forces that are perpendicular to that motion have to be balanced, and that means that the y component plus the normal going up has to be equal to Fg going down. All right? So here to find the y component, right, if we draw our force triangle, we'll see that the y component is opposite the 30 degrees, which means we've got to use sine. So that's going to be 40 times the sine 30 plus the normal is equal to Fg, and that's 3 times 9.8. Okay, so now I'm just going to go 3 times 9.8 minus the 40 times sine 30. And I get here that the normal force is going to be equal to 9.4 newtons. Okay, and now I'm in luck. Now I can easily go find the work done by friction. It's going to be the force of friction times the displacement times cos of the angle between the force and the displacement. The frictional force is going to be mu kn, right? So that there. So this is going to be 0.1 times the 9.4, okay, the normal force that I just found. The displacement is going to be the same as before, 5. And now again, friction is in the opposite direction to the displacement of this object. This is cos of 180. Okay, so 0.1 times 9.4 times cos of 180 gives us negative 0.94 joules. Okay, so friction didn't do an impressive amount of work here, but it did try its best. Okay, and then to find the net work, we are just going to add up the work done by all the forces that did do work, and that's going to be the 173.21 from the applied force minus the 0.94 from friction. And so you will get that the net work done was 172.27 joules. Okay, so here you might notice that I didn't bother to find the work done by gravity, nor the work done by the normal force. And that is going to be because for those, I know that the displacement is going to be perpendicular to the actual force, which means that those forces did zero work. They did not help, nor did they hinder this 3 kilogram object on its journey along that 5 meter displacement. All right.